Hi there, my name is Brandon, and welcome to the next video in my series on basic statistics. If you are new to the channel, welcome, it is great to have you. If you're a returning viewer, it is great to have you back. If you like the video, please give it a thumbs up, share it with classmates, colleagues, or friends, or anyone else you think might benefit from watching. You can also find a link in the description below to all of my playlists, of which there are 19 now. It's basically a table of contents. And of course, please hit subscribe and click the bell notification if you haven't already. So now that we are introduced, let's go ahead and get started. So this video is the next in our series on non-parametric statistics, or non-parametric methods. In the previous video, we learned about the Kruskal-Wallis test. And that test is essentially the non-parametric version of the one-way ANOVA. Now this video is about the Friedman test. And the Friedman test is essentially the non-parametric version of the two-way block ANOVA. Now, of course, I have videos on the one-way ANOVA and the two-way block ANOVA, which you can find in the description and possibly in the note card at the top if you need a refresher. So in this video, we will learn the concepts behind the Friedman test, and then we'll go into Excel and actually calculate it. So let's go ahead and get started. So first, a bit of background to set us up. Now, comparing more than two independent samples with a blocking variable using a parametric test would lead us to use the two-way block ANOVA procedure without replication. In that case, we would test to see if the means of the samples are equal while accounting for variation in the blocking variable. So remember, the blocking variable sort of siphons away error into the blocks so we can focus on the error of the model, or the SSE. The non-parametric version of the two-way block ANOVA is the Friedman test, and it's very similar to the Kruskal-Wallis test. So if you watch the previous video, when we go ahead and calculate the test statistic in the Friedman test, it will look a little bit familiar to the Kruskal-Wallis test. The Friedman test allows us to compare more than two populations with a blocking variable without having to assume the observations are normally distributed. Again, that's the point of non-parametric statistics at a fundamental level. Therefore, we use the ranks of the observations, or the locations of the observations in the dataset, not the actual values themselves. So here is our problem for this video. I call it Mumbai Starbucks. And remember, we'll go into Excel towards the end and actually calculate it. And there will be a link in the description where you can grab that file and follow along. So here is our problem. 15 students from Mumbai, India, who often study at Starbucks, like me, were asked to provide ratings for 4 stores. Now, each store or treatment, so in this case, the treatment is the store, is being rated by each student. And in this case, the students are the blocks. So each student was asked to review the Churchgate store, which we'll call C, Netterman Point with N, Taj Mahal Palace, T, and Horniman Circle, H. So 4 stores in the same general area. And each student will rate all 4 stores. The survey covered 5 criteria: cleanliness, service, facilities, drink quality, and food quality, each on a scale of 1 to 5. Now, the lowest possible score for each store is 5. That would mean they got a 1 on each of the 5 criteria. And the maximum score is 25, and that would be if they got a 5 on each of the 5 criteria, or a perfect score. However, the score itself is not important. What we're going to work with are the ranks of the stores. And this should make sense. When we're doing a survey like this, there's no way to know or assume or even think that the ratings are going to be normally distributed. It's basically a Likert scale or a survey. So in this case, a non-parametric test is actually more appropriate. So this is what we're asking. Is there a difference between the stores while taking into account the raters? So we're going to sort of factor out the rater variability using blocks so we can focus on any differences between the stores. And again, that mirrors the basic idea of a two-way block ANOVA. So here is our simple general hypothesis. The null hypothesis is that all treatments, in this case all the stores, are the same. The scores are the same. The alternative hypothesis is that all treatments are not the same, or in this case, that there's at least one store that's different from the others. Could be 2, could be 3, but at least one is different from the others. So rejecting the null hypothesis means that there is a difference among the blocked treatments. it does not tell us where that difference is among the treatments. That would require some sort of post hoc analysis, which I might get to later in this playlist for the non-parametric methods. Now, all Friedman tests are one-tailed tests because it uses the chi-square distribution to obtain a p-value. And over the next few slides, you'll see why that is. So here are a few visuals so we can understand what's actually going on in this test. Do our stores look like this? Is the first treatment over here on the left? Is the second treatment towards the middle? Is the third treatment all the way to the far right? And is the fourth treatment here in the middle, kind of where treatment 2 is? And again, I'm saying treatment here because that's the technical term, but in our problem case, those are stores. Or do they look like this? Are treatments 1, 2, and 4 kind of together over here on the left, and treatment 3 over here on the right by itself? Or do they all sort of line up together? Now, they're not going to probably line up identically. That's very unlikely. But we're talking about, are they identically statistically speaking? Now, when it comes to the null hypothesis, this lowest visual is what we're testing. Remember, the null hypothesis states all treatments are equal, or are statistically equal for that matter. That would look like the visual on the bottom. Now, if our data looked like the middle visual, we would probably reject the null hypothesis, because while treatments 2, 1, and 4 seem to be close together, treatment 3 is off by itself. And if that's different than the other 3, we would probably reject the null. And of course, in the top visual, we would almost certainly reject the null. So what we have here is sort of a scale. On the top, we would probably reject the null hypothesis. They look very different. On the bottom, we would probably fail to reject the null hypothesis because they look to be fairly equal. And again, these are just visuals to help us conceptualize what's actually going on related to the treatments and our hypothesis. Okay, so how do we do the Friedman test step by step? 1. We place our blocks into the first column. In this case, those will be the students. 2. We place our treatments into K columns. In this case, those would be our 4 stores. In K additional columns, so we have 4 columns for our stores, we would create 4 more columns, and then we would rank the K treatments. We would rank the stores across the blocks. This is where this is different, and I'll show you some visuals here to help. In the previous examples in non-parametric statistics, we are almost always ranking down the columns. But in this case, we are ranking across the blocks, and we'll see how that works. Now, for any tied ranks, we use the average rank. In Excel, we use the rank.avg ascending. We sum the ranks for each treatment at the bottom of the columns. We then calculate the Friedman statistic, which is F sub R. You might also see it as F sub T or something similar, depends on the book you're using. Then we compare the p-value to the chosen alpha level, which in most cases is 0.05, using the chi-square distribution. So the next few slides are some visuals to help you understand how this calculation works and points out some interesting facts about the Friedman statistic so you can sort of know where the test is actually coming from. So here are some generic data. You can see that along the top we have our 4 treatments, T1, T2, T3, and T4. In the first column we have 5 blocks, A, B, C, D, and E. Now what we have here is an extreme case where all 4 treatments are rated the same order by each block. So you can see that block A has T1 as 1, T2 as 4, T3 as 3, and T4 as 2. Again, those are ranks. Then block B has the same, C has the same, and also D and E. So this is an extreme example. So we rank across the columns. You can see that we don't rank down. If we ranked down, T1 would be 1, 2, 3, 4, or 5. We rank across. Then we sum down the column. So we can see that the sum of the ranks for T1 is 1 plus 1 plus 1 plus 1 plus 1, which is 5. The sum of ranks for T2 is 20. For T3, it is 15. And T4, it is 10. In the Friedman test, we then would square those sums. So 5 squared is 25, 20 squared is 400, 15 squared is 225, and 10 squared is 100. So what can we deduce from this? First, the minimum is 5. So if T1 had a rank of 1 from every block, the sum would be 5. So the minimum there is 5. The maximum would be 20 in this case. So here we have T2 had a rank of 4 across all the blocks going down, so the sum is 20. Notice the sum of those ranks is 50. So the sum of all the ranks in this table equals 50. Now if we take the sum of ranks for each treatment and then square them and then add them together, we have 750. So remember these numbers: minimum of 5, maximum of 20, the sum of all the ranks in the table is 50, and then the sum of the squared sum of ranks is 750. Now let's look at a different case. So now look at this example. In this case, all of our ranks are sort of mixed. So if you look at block A, T1 is 1, T2 is 2, T3 is 3, and T4 is 4. Again, those are ranks. Now if we go down to block B, T1 is now 4, and T2 is 1, T3 is 2, and T4 is 3. So again, we're ranking across within each block. Now the sum of the ranks for T1 is 11. Again, we're going down. For T2, it is 14. For T3, it is 13. And T4, it is 12. Now notice the sum of 11, 14, 13, and 12 is still 50. So it does not matter how the ranks are arranged in this table. So as long as we have 1, 2, 3, 4 in some order across the block for each treatment, it will all add up to 50 regardless. Now if we take the sum of the ranks for each column, which in the first case of T1 is 11, and then we square that, it's 121. We do that for each column and then add those together, we now have a sum of 630. That's different. What was the number in the previous slide? It was 750. So that number went down considerably when the sum of the ranks are mixed together like we have here. Now of these two cases you have seen so far, which one do you think would result in rejecting the null hypothesis and failing to reject the null hypothesis? Again, this is conceptual data, but compared to the hypothesis statement, how do you think each one of these two examples would measure up compared to the hypothesis? Well, remember, the null hypothesis states that all of our treatments are equal. Now, look at this one. We have a sum of 11, a sum of 14, a sum of 13, and a sum of 12. That is pretty equal. So, theoretically speaking, we would probably fail to reject the null hypothesis. In this case, we see here. In the previous slide, where we had 5 and 20 and very spread out numbers, in that case, we would probably reject the null hypothesis because there are obviously differences among those treatments. In the extreme example before, we would probably reject the null hypothesis. In this case we see here, we would probably fail to reject the null hypothesis because the sum of the ranks for the 4 treatments are very close together. Now this slide is really at the heart of what's going on in the Friedman test. Remember, the sum of the ranks is always going to be 50. If the 4 treatments were the same, we would expect the sum of the ranks for each treatment to be the average of that. 50 divided by 4 is 12.5. So we have 12.5 for the sum of ranks for T1, 12.5 for T2, and so on and so forth. This is the fundamental null hypothesis. So fundamentally, what we are asking here is this. If the 4 treatments are equal in their ranks, or the sum of their ranks, we would expect the sums to be 12.5 or pretty close to 12.5. That is our expected. Now we compare this expected sort of ideal to what we would have in our actual data, which is what we observed. Now remember, in most cases, when we're talking about expected versus observed, we use the chi-square test. And this slide here is fundamentally why we use the chi-squared. We're going to test this, what we'd expect if all 4 treatments are equal, to what we actually observe in our data, and then make a judgment on our hypothesis. Now I'll also point out here that the sum, 625, which is 156.25, that's just 12.5 squared for each column. So 156.25 times 4 is 625. That's actually the minimum for that value, because this is the ideal case where all four sums are equal. So here is the sampling distribution test statistic. So the Friedman statistic, or the F, equals this formula here. Now, it looks kind of nasty, but it's really not that complicated. And when we go into Excel, you'll see that it's just basic math. We just have to keep our order of operations together. So K equals the number of columns or treatments, B is the number of rows or blocks, and T squared sub J is what we did in the previous slides. It's the squared sum of the ranks for the sample treatment. So that is just the square of the sum of the ranks for each treatment. So what we do there in the middle is we actually iterate through each sample. So remember when we squared the sum of the ranks and then added them together? That's what that term there represents. So for the test, we ask this. If our test statistic, so F sub r, is greater than the chi-square value at our chosen alpha level with k minus 1 degrees of freedom, if that is larger on the left than on the right, we'll reject the null hypothesis. And we would say that in this case, 4 treatments are not equal. And of course, we could also use the p-value method, where we find the p-value for the chi-square statistic. We compare that to 0.05. If it's below 0.05, we reject the null hypothesis. If it's greater than 0.05, we would fail to reject the null hypothesis. So remember that using the test statistic or the p-value, those are two sides of the same coin. It's just two different ways of representing the same thing. And I'll actually show you a graph at the end to point that out to you. Okay, so let's go ahead and go into Excel and calculate the Friedman test for our Mumbai Starbucks example. Okay, so here we are in Excel. Let's go ahead and calculate the Friedman test or the Friedman statistic. Now remember, this file is available in the description, so if you want, you can pause this video, go download it, open it up, and follow along step by step if you want to. So I went ahead and set up the spreadsheet to make things go a bit quicker. In the first column, we have our blocks. These are our students, so student 1 through 15. Columns B through E are our 4 stores. So student 1, when they went to the Churchgate store and filled out the survey, gave them a 20 out of 25. Then at some point went to, say, Taj Mahal Palace store and gave that store a 17 out of 25, and so on and so forth for the other 2 stores. And then the other 14 students did the exact same thing for all 4 stores. So the first thing we need to do is find the rank for all 4 stores for each block. And we do that using the rank.avg function. So we'll start in F2 to find the ranks across all 4 stores for each student or block. So equals rank.avg, the number we want to rank, which is 20 in this case, comma, what we're ranking against, which are all 4 stores, again, going across, comma, 1 for ascending and close. I'll have to make one change here to make dragging across and down possible. I'm going to go here in the B2, hit F4 a few times, so it's $B2. Do the same thing for the E2. Hit that F4 a couple times, a few times, $E2. Now, why did I do that? Doing this locks me in the columns B through E, but will allow the row to change. That's why there's no $ in front of the 2. So that'll make dragging across and down possible. And that makes sense here. So the Churchgate store is ranked 3rd out of these 4 stores. Netterman Point would be 1, Taj Mahal Palace would be 2, Churchgate would be 3, and Horniman Circle would be 4. And then, of course, when we drag across, we'll see that. Now, we can actually, because we did the correct cell references, we can actually drag all the way down for all the students, and there are all of our ranks. Isn't that nice? Now, remember, we need the sum. So equals sum, and we need all the ranks above that, close. So that's 33. The sum of the ranks for the Churchgate store is 33. Drag across. Now we have the sum of the ranks for all 4 stores. Now notice here, just eyeballing this, we can see that the sum of the ranks for Netterman Point is much lower than the other 3. So 19.5 versus 33, 42, and 55. So we would, using sort of common sense face value, say that Netterman Point appears to be quite a bit different. But again, we won't know that for sure until we actually go ahead and conduct the test. So down here in H20, I have 4 values I want to find, and these correspond to the slides that we did in the actual video before this. You don't need these to do the Friedman test, but conceptually, I just want to point out what is actually going on. So what is the minimum sum of ranks we could have? Well, imagine that Churchgate all had a rank of 1 all the way down. So 1 15 times would be 15. So the minimum sum of ranks would be 15. What is the maximum sum of ranks? Well, in the first case, it's 15 times 1. What's the maximum rank we could have? Well, that's 4. So this is 15 times 4. You can do it in your head if you want, but 15 times 4 is 60. So the lowest sum of ranks we have here could be 15. The maximum it could be is 60. Those are the two extremes. Now, what are the sum of all the ranks? We can do that a few ways. So I'll sum the totals. We could actually sum the ranks above it if we wanted. So the sum of all the ranks here is 150. Now, what is the expected sum of ranks if all of these are equal? So that's 150 divided by how many treatments we have, which is 4, is 37.5. So if our null hypothesis were true, these values here, our sum of ranks, should be all around 37.5, because that is the sum of our ranks divided equally among all 4 treatments. So keep that in mind. Now we'll hop up to L1. So the number of blocks that we have, again, we could do that by hand. I'll use count, because I like using functions. I'll use count A, 15. How many treatments do we have? Well, equals count. We could do this a few different ways. I'll just take one of the rows. So we have 4 treatments. We know that. Now we can start calculating the actual parts of the test statistic. And this is where things get a little funky. So let me make some room here so we can see as we type. There we go. So I want to focus on this blue part right here. So we'll do that as in part 1. So we have 12 divided by B times K times the quantity K plus 1. That's actually very straightforward. So equals 12 divided by, and we'll close parentheses here, B, which is up here, times K, which is below it, times the quantity K plus 1, close, close, and we have 0.04. Very easy. Now what about part 2? Here we need the sum of the ranks that we've squared. So first we need to square all of our sum of ranks down here at the bottom of each column. So the first one is equals this 33 down here below Churchgate squared. So 1089. Do the same thing for the rest. And there we go. Now we got to sum all those up. This is the summation sign. So what we just did was find t squared for each of our j's. J's are our columns. Now, with the summation sign, we just add those up. So equals sum, select those, done. So now part 3. Again, this is very simple. It is 3b times the quantity k plus 1. So we'll go ahead and do that. So equals 3 times b times the quantity k plus 1, close, enter. So now we just put it all together. So now we put all 3 parts together to find our test statistic. So here I have f sub t. In the slides I had f sub r. I changed it on purpose just so you know that they mean the same thing. In some books you might see f sub r, some f sub t. In other books you might see something completely different, but it means the same thing. It's just the Friedman statistic. Let's go ahead and put parts 1, 2, and 3, or the blue, orange, and green together to find our test statistic. So equals, parentheses, everything in the blue, right there, times the sum of our squares here, which is the orange, close parentheses, minus part 3, which is green. Hit that, enter. So our Friedman statistic, or test statistic, is 27.54. Well, what does that mean? So we need something to compare that to, and that is our critical value for the chi-square. To do that, we use one of the chi-square functions in Excel. So equals chi-square inv.rt, so that's inverse right tail, probability is 0.05, or of course we could have just selected our alpha value, either way. Degrees of freedom are k minus 1, so we could actually do that. We could do k minus 1, close, enter. So our critical value is 7.81 and so on and so forth. So as we can see here, our test statistic is way, way above our critical chi-square value. So we know already that we're going to reject our null hypothesis. Now we could just go ahead and stop there, but I'll go ahead and calculate the p-value so you know how to do that. For this, we use another chi-square function. So equals chi-square dist.rt. Our x is our Friedman statistic. Degrees of freedom, same thing as k minus 1, so we could go up to k minus 1, close. And we can see that's a very, very, very small value. So 0.000004. I think I counted that many zeros correctly. So obviously that is lower than 0.05. And again, that is evidence that we would reject our null hypothesis. So I usually like to set up an if statement at the end of these to theoretically make them automated if you were to want to. So we'll say reject null, and we'll make a function equals if, you can do this one of two ways, but I'll say this, if our Friedman statistic is greater than our critical value, then yes, otherwise no. And actually I'll put greater than or equal to. Hit enter, and therefore yes. So we would reject the null hypothesis because the critical value is obviously 7.81 or about 7.815. The Friedman statistic is 27.54. That's obviously a lot larger. And of course our p-value is very, very small. Now we'll point out if you do this in software, you might get a slightly different number for the Friedman statistic. Here it's 27.54, but in another software program I use actually within Excel, it gives something like 28.88. That's just because of the software differences. There's neither one's wrong. It's just because of the algorithm in the software versus here doing it by hand. So let's go back into the presentation and finish this video up. So here are our results. Our test statistic, or our Friedman statistic, was 27.54, which is obviously much greater than our critical chi-square value of 7.815. The p-value is less than 0.001, and therefore, of course, we would then reject the null hypothesis. So visually, it looks like this. So over here on the right, we have a chi-square distribution. In the shaded area of this graph, two things are represented, again, which are two sides of the same coin. So the crit value there is the 7.815. That's the value along our x-axis. The shaded area is our alpha of 0.05. That is the area to the right of 7.815. So the area is the shading, the 7.815 is the actual value where the shading begins. You can see that our test statistic, which was 27.54, and over here on the right is 28.88, the difference between those two numbers is just software algorithms. There's a slight difference in how some of the softwares do these non-parametric stats, but they're very close, and obviously it's way higher than 7.815, so it doesn't really matter. So if you see a discrepancy between how you calculate this by hand and what your software produces, it's just something that happens because of the slight differences in software. Either way, our value over here is way over to the right, well beyond that 7.815. And of course, that's where our p-value is so small, because our p-value represents everything to the right of that green dot. So again, this is the chi-square distribution showing visually our critical value, or alpha of 0.05, and then where our Friedman test statistic falls relative to that. And of course, we would reject our null hypothesis. So that wraps up this video on the non-parametric Friedman test. So again, the Friedman test is sort of the non-parametric equivalent of the two-way block ANOVA, where we're testing across treatments, but we have a blocking variable going down our columns. And again, doing this method helps us sort of focus in on the differences between the treatments because we can actually sort of filter out the differences between the blocks. So thank you very much for watching. I wish you all the best of luck in your studies and in your work, and I look forward to seeing you again next time. Take care. Bye-bye.